Okay, hi. So we continue our discussion on Fourier series. We are towards the end of this Fourier series chapter. So we will now see the real application of Fourier series. Okay, why do we looked at Fourier series? We saw the representation. We discussed something about convergence, but now let's see why Fourier series is useful in practice. Okay, so again we will see. Uh, we will see that the input signal, if it is a complex exponential e raised to st, we saw that there is a relationship between complex exponentials and LTI systems, in that the complex exponentials are eigenfunctions. For example, if this is my x of t and I give it to an LTI system and I get a y of t, so the output, if you give e raised to st as input, will be the same e raised to st multiplied by a constant h of s, right? So because this is an eigenfunction, this is the same input, you give one input, you get the same input as output scaled by a factor, just like a eigenvalue eigenvector. And if you give an eigenfunction as input, you get the same function as output with a scaling factor. But here the scaling factor h of s is a function of s. S is the input with respect to the complex exponential which we are giving as input. So by when we say h of s is constant, here we mean it in the sense that h of s does not depend on t. It is independent of time, but it is a function of s. This is a parameter of your input, and the output is a function of that parameter. But this h of s is independent of time. So no matter at what time you apply the st, whatever is the value of t, you will get the same output, h of s e raised to st. Okay, so this h of s does not depend on time. And but now what is this h of s? H of s we said was this h of tau e raised to minus s tau d tau. This was covered in the earlier part of the Fourier series chapter, where h of t is the impulse response, right, of this LTI system. The impulse response is the response of the system to the unit impulse function. The same is the case with discrete signals, discrete complex exponentials. Z s to n is our complex exponential, where z is in general a complex number. Here also s is in general a complex number. So if you pass this to the LTI system, you get a y of n. Again, this is an eigenfunction. And how it is an eigenfunction? If you apply the convolution operation, you just apply the h of n convolve, z of n convolve with h of n, then you will get the answer in terms of z of n. So where the h of z is now the scaling factor for the eigenfunction. Again, z is independent of n. So h of z is independent of n. It depends only on z, where z is the input, the parameter of the complex exponential. And the h of z is defined in an analogous manner, which is h of k z raised to minus k sum, where h of n is the impulse response. Okay, so essentially what you need to remember is, if a complex exponential is given as input to an LTI system, the output will be an eigenfunction, and it will be in terms of the same input, whether it is z, it will be in terms of the same input here, sorry, not this. It will be in the same in terms of the same input, whether it is the discrete case or the continuous case. Okay, here also this is in terms of the same input, e raised to st, this is also e raised to st. And you should also understand what is the idea of the impulse response. Now, when in general, your z and your s could be, s and z could be any complex number, but in particular when s is purely imaginary, or when that is when s is equal to j omega, we have the input, your x of t now becomes e raised to st, which is e raised to j omega t. So this is essentially a complex exponential with frequency omega. Okay, this has no real part, so this is purely complex, and this is a complex exponential, which is the same complex exponential which we have seen in the Fourier series. This is a complex exponential with a frequency omega. And when you substitute this value into the h of s, which we saw here earlier, the same h of z, s h of s, when you do that and when you compute the h of s, you find that you apply the same formula to find h of s, and this particular h of s, or in this case h of j omega, is a function of omega, and it has a particular name called the frequency response. This is the frequency response of the LTI system. Later when you study the Fourier transform, you will realize that the frequency response is nothing but the Fourier transform of the impulse response. That we will come to that later. Okay, but essentially you apply the same thing here. You just replace your s with j omega, and your this h of s formula becomes h of j omega, and this is a function of omega. See, I said this h of j omega is independent of t, the time. It is independent of t, because if you see this expression, we are averaging out all the time. Okay, this is done over dt. This is done over all time, and hence the time variable gets averaged out, and this becomes a function of only omega. So this is the frequency response. Same is the case in the discrete time, when z is in particular e raised to j omega, then zn becomes e raised to j omega n, and your h of z, which we computed here earlier, h of z, that h of z in this particular case, it takes this form, and in the discrete time case, this is known as the frequency response. Similar in the continuous time case, similar in the continuous time case, h of e raised to j omega is a function of omega, and it is independent of n. It does not have an n. Okay, so the notation here, h of j omega and h of e raised to j omega, in particular it is a function of omega, but we write it as h of j omega and h of e raised to j omega to emphasize that this function could be in general a complex function. Okay, all that is fine. Now we understood what is the frequency response. Now the question is, why should we know about the frequency response? Why should we care? Okay, why is the frequency response useful to me? That is where the real power of the Fourier series representation comes. Now suppose x of t is a periodic function, and it has suppose it can be represented by a Fourier series. And now we pass h of t into a system h of t, into an LTI system h of t. Now the system, we know that x of t, when you give it to your h of t, is going to be an eigenfunction, because x of t is represented as a linear combination of complex exponentials. So this complex exponential is an eigenfunction to the LTI system, and so a weighted sum of complex exponentials will, by applying the superposition property and the time invariance property, you can find a value for the output y of t as, it's nothing but the same scaling factor. Now e raised to j k omega naught t will give you h of e raised to j k omega naught into the same input. So these two things are the same, except that now this is our h of s or h of z. In this case, the same h of s, h of z, which we saw earlier, and the same h of s which we saw earlier. That is the same thing here. Here, except that we are restricting the values of z or s, because s we are here, when you represent it by a Fourier series, s is not any complex number. S is a harmonically related complex exponential with respect to the fundamental omega naught. Okay, they are those frequencies of those complex exponentials are integer multiples of omega naught. So now essentially what this means is, this ak h of e raised to j k omega naught forms the Fourier series representation of y of t. Right? So this is the Fourier series coefficients of y of t. So essentially what we have done is, we have an input. That input is getting transformed by this particular factor. Right? So this is my input that has now become transformed into this as the output, and this fellow here will tell you how the output gets transformed. Okay, so essentially this property can be used to design LTI systems that modify the input in a desired manner. We will see an example. Now suppose you are all aware of audio signals, right? In audio signals, when you listen to songs, there are multiple frequencies are there. There are now, for example, if you are into music, or if you have a reasonably good phone or a music system, you know that you can get controls by which you can increase the bass, that is the low frequencies, the low frequency sounds like the bass guitar or a drum or something, which is fundamentally low frequency. And you can also, if you want, by change the treble. The treble is nothing but the high frequencies. So high frequencies, for example, in some instruments like piano or flute might have high frequencies, whereas drums and bass, guitar, etc. are low frequencies. So the bass is the low frequency and the treble is the high frequency. Now suppose I have an audio signal x of t and I represent it by a Fourier series ak. So this xt transforms to ak, okay, by the just by taking the Fourier. So ak is x of t is represented by a Fourier series where ak are the Fourier series coefficients. And suppose this is the output yk, it has got the Fourier series coefficients bk. Now suppose this is the ak. This is the Fourier series of the Fourier series representation of the input. Okay, so this is my value of k. So you can see that this essentially means that your x of t has got all these frequencies which are present. Okay, where all these 0, 1, 2, 3, 4, 5 are all the multiples of the k omega naught, right? Where omega naught is the fundamental frequency of xt. So these are the Fourier series representations of xt. Essentially, this is the spectrum of xt. Now, suppose I design my h of h e raised to jk omega naught in this way. Okay, so I have this particular form. This is my h e raised to jk omega naught. I am giving high values to 0, 1, 2, 3, and I am giving very low values to 4, 5, 6. So essentially, and then we also saw that. So what we did is we are just applying the output. The Fourier series of the output is nothing but the input Fourier series scaled by these h of e raised to jk omega naught. So that is, these are the h of e raised to jk omega naught. So now when you, this is these Fourier series coefficients, the input Fourier series coefficients are scaled by these Fourier coefficients. And essentially what do you get? You will see that the 0, 1, 2, 3 are getting high values because these are boosted up and these are boosted down. So these have become low. So essentially what we have done is we have manipulated the Fourier series of the input so that we are forcing the low frequencies, here in this case 0, 1, 2, 3 to be high, and we are forcing the high frequencies to be low. So essentially what we have done is we have done a bass boost, right? We have increased the high frequencies. We have decreased the high frequencies and boosted up the low frequencies. So a drum might sound more thumpy, tum tum, like that kind of sound. So essentially, so this representation here, you can see here, no, this is like this. This is essentially what this looks like. So that is what is ideally represented here by what is this is a low pass filter. Why? Because by looking, this is the frequency response of the low pass filter. It basically says that we are giving high values to low frequencies. These are the low frequencies, this is 0, and these are the higher frequencies. So we are giving high values to low and we are reducing the values of high. So essentially this is the pass band and this is the stop band. So for example, if your input is a signal like this, after you pass it through this low pass filter, your input will become like this. Essentially, all the high frequency components have been removed. Okay, so in practice in audio signal processing, this you must have seen this mixing consoles if you've seen pictures of audio recording studios where the music director sits and records the music while it is being sung by the singer and the instruments. So now by varying so this set of knobs here control the frequency response. So by the music director or the sound engineer can, by varying these controls, he can get different characteristics to the final recorded sound. Okay, so for example, if these represent This gives an intuitive way to manipulate the frequency spectrum. So if these knobs are all high and these knobs are all low, then you get a low pass filter, assuming that these are for the low frequencies and these are for the high frequencies. And similarly, if these are low and these are high, means you get a band pass filter with the spectrum looks like this. And similarly, if these are all low and these are high, so you can get a high pass filter. So by manipulating the audio frequencies, the music director can get the desired effect. So this is an example of the frequency response of a high pass filter. So you can see that the low frequency regions are attenuated and the high frequency regions are boosted up. So if an input like this is given, you get an output like this, where only the high frequency parts are transmitted. Fine. So this is the output. This is shown it in time. Okay. So this is, remember that this representation is in time. We are showing the signal with respect to time, and this is the frequency response, which is shown with respect to frequency. So this is in the frequency domain. It's just two different views. Okay, if you look at it in frequency, it is like this. If you look at it in time, it is like this. And only those portions of the signal which have high frequency content are passed through the high pass filter. Now we will look at another filter, which is again there in the textbook, which is a differentiating filter. So this is the relationship. This is a continuous time filter. YFT is a derivative of the input. This is the relationship between the input and output. So if you give x of t as e raised to j omega t, my y of t becomes this j omega e raised to j omega t. And if you plot the impulse response of this system, your h of j omega, if you compute it using the formula which was there earlier, your h of j omega will look like this j omega. It is a complex value. Okay, so we can plot the magnitude, which looks like this, and we can plot the angle, the phase, which looks like this. Okay, so is this a high pass filter or is it a low pass filter? You can see that since the low frequencies, which are around 0, are attenuated and the high frequencies are boosted up, these are the high frequencies, so this is a high pass filter. So how is this filter useful? So it's this kind of differentiating filter is useful in images. For example, now suppose you consider an image signal x of t1 t2, where t1 t2 are not time here. Actually t1 t2 image is a function. It's a 2D function of two spatial coordinates, x and y, x coordinates and y coordinates. Okay, so this is an image and this is an image signal. Now suppose this is, see this part of an image which is an edge. Okay, this is a vertical edge in an image. Now if you go through this line, you will see that at these points the values are some value, then it suddenly increases here or decreases here in this case, and it becomes up again. So that is, so if you go along this line, you will see it like this. The pixel values are going to be high, then suddenly it becomes low, suddenly it becomes high and continues to become high. Here we are assuming that black represents low and white represents high. Okay, so now if you apply this differentiating filter into this, so this is the time domain or the spatial domain representation of an image, of this particular edge. So these are basically the pixel values. So if you give this signal as input to a differentiating filter, you will see that it passes only the high frequencies. So only these portions are passed, right? Only these portions are passed by the high frequency, because only this part and this part are the high frequencies. So this part is nothing but the starting of the edge, and this is the finishing of the edge, right? So you can also represent the gradient of an image in this way, because the image is a two-dimensional function. You will have two partial derivatives, the dou f by dou x and dou f by dou y. This is the derivative with respect to x with the x axis, the derivative with respect to the y axis. And so now if you apply this differentiating filter to an image, now this image of a zebra here, so this is dou f by dou x and this is dou f by dou y. So you can see that when you do the dou f by dou y, all the horizontal lines are emphasized, so as you can see here. Whereas if you do dou f by dou x, all the vertical lines are emphasized, as you can see here. And so if you take the magnitude of this gradient as given by this, you will see that essentially what you have done is given this input, and if you apply the differentiating filter and find the magnitude of the output, you will get an image where the edges are emphasized. So these kind of filters are used in image manipulation tools, like for example, if you want to, in tools like Photoshop, if you want to apply a particular transformation to a part of the image, you want to make it sharper or you want to make the edges look better, then this kind of filters can be used to various parts of the image. So the book also talks about other filters, RC circuit low pass filter, which is a continuous time filter, RC circuit high pass filter, which is also a continuous time filter. Then the book also talks about recursive discrete time filters, which are essentially IIR filter, and non-recursive discrete time filter, which are essentially FIR filter. So we touched upon FIR and IIR briefly in the initial chapters, in the second chapter when we studied LTI systems. So you can have a look at that. But now we will just look at one particular example of a discrete time filter, which is a moving average filter. Okay, we have seen the moving average filter earlier when we were studying systems. So the moving average filter looks like this. So you have the this is the relationship between input and output. Your output at n by n is nothing but the averaged value of the input over minus n and n with respect to n. So essentially it looks like this. If this is my input x of n, at this particular point the output y of n at this n is nothing but you take n points before and n points after the small n, so that is these n points before and n points after this thing, and take and replace this x of n with the average value. That is essentially what this is doing. So is this filter a low pass filter or a high pass filter? Is a moving average filter a low pass filter or is it a high pass filter? To answer that question, you have to compute its frequency response. Okay, so now let's take for example a 3-point moving average filter. 3-point moving average filter where you have x of n, you take one sample before it and one sample after it, and you divide it by 1 by 3 because you are averaging over 3 samples. So what is my h of n? To find out the h of n, you have to give your x of n as a delta function, which now becomes del of n plus 1, del of n minus 1. This is my h of n, and your frequency response now becomes h of e raised to j omega is this applied to the impulse response. This is the impulse response, and we do e raised to minus j omega n, you will get the h of e raised to j omega. So if you substitute those values here, and if you use the shifting property of the impulse, we are going to use the del of n plus 1 plus e raised to minus j omega n is nothing but e raised to j omega into del of n plus 1. This is the shifted and scaled impulse. And if you apply the shifting property, and the summation will be removed, and your output will now become, by your h of e raised to j omega will now become 1 by 3 into e raised to j omega plus 1 plus e raised to minus j omega, which is nothing but 1 plus 2 cos omega. So the 1 plus 2, this is your h of e raised to j omega, which is the frequency response. So the frequency response of this is in general a complex number, right? But in this case it is it is not complex, it is real. So now if you plot its magnitude of the frequency response, if you plot the magnitude of the frequency response, you will see that the frequency response will look like this. So this is the omega axis. So this is a discrete time system. So we said that in discrete time systems or in discrete time signals the frequencies separated by 2 pi are identical. So from minus pi to plus pi gives you all the frequency characteristics of the system, and after that it begins to repeat, right? So what is there from 0 to 2 pi is same as from 2 pi to 4 pi and so on. Similarly, if you look at 0, it is symmetric about 0. So from minus pi to plus pi gives you the complete frequency response, and this is part of the repetition. This part and this part are part of the repetition. So you can see that if you apply this this is nothing but the plot of this one, and you can see that it emphasizes the low frequencies around 0, and as you go further away from 0, the attenuation comes down. So these are your these coefficients we saw here, no? These coefficients, I mean, this h e raised to j omega coefficients are what is shown here. Here, of course, here we have there is some abuse of notation here, because we are expecting discrete values, because we are assuming that these are represented as a Fourier series, and hence the the values of the frequency response will be integer multiples of the omega naught, will be k omega naught. But in this case they have shown it as a continuous plot, because this is just to show that how the frequency response looks like. Okay. So this is so essentially the moving average filter is the low pass filter. So a more generalized version of the moving average filter is when you have n points before and m points after x of n, and in this case there are two plots in the book which shows m plus n plus 1 is 33, n plus n plus 1 is 65. So essentially, so the averaging here in this case is done over 33 values. Okay, so if you have your x of n, you take some values here, some values here. This total length is 33 here in this case, and the filter looks like this. And if this is a longer filter, m plus n plus 1 is 65, so the averaging is done over 65 values, and this is the impulse response. Okay, so I mean, this is the frequency response. Sorry, this is the frequency response. So you can see that in both the cases it is a low pass filter. It will be interesting as a homework. You can find out what is the impulse response of this generalized moving average filter. Okay. So by adjusting the size of the filter with n plus m plus 1, the cutoff frequency can be varied. See, so here the cutoff frequency is here, whereas here the cutoff frequency is here. So by manipulating the length of the filter, you can choose your cutoff frequency. And in general, filter design itself is a complete topic in itself, but in general FIR filters, the book also talks about FIR filters. Okay, FIR and both IR, both examples are there in this chapter. But in general, FIR filters of a given length cannot provide the sharp cutoff of an IR filter. So if you see this filter here, see, if you say I want to cut off all values after this, okay, then does this filter achieve it? Yes. For example, for most of the frequencies within this to this is allowed to pass, but now some of the frequencies after this are also coming here. Okay, so this is because of these ripples which are there in the filter. These are some characteristics of this particular filter, because the length of the filter is so small, because we are only using 3 samples as input, no, because we are only using 3 values, xn minus 1, xn and xn plus 1. So essentially the length of this moving average filter is 3. It's a 3-point average filter, so the cutoff will not be very sharp. Okay, it will give you a broad pass band. But if you want a very sharp cutoff, you will either need to increase the length of the filter, or you will need to go in for an IIR filter. So FIR filters cannot in general provide the sharp cutoff of an IIR filter, but the pluses and minuses of FIR and IIR depends on the application. But in general, FIR filters are always stable, because the impulse response is finite. Okay, it's a finite sum. Whatever you do, it's a finite sum. Whereas IIR filters, if not designed properly, could become unstable. Okay, the summation may not converge, because it is an infinite impulse response. So we have only touched upon these topics, but I hope you got an essence of how useful the Fourier series is, and how the output can be manipulated by manipulating the output by manipulating the frequency response of the system. So if you give it an input with a particular frequency response, I mean there is an input which has a particular Fourier series spectrum, you have a system which has a particular frequency response. Now by passing this input to this LTI system, the frequency characteristics, the spectrum of the input is modified according to the frequency response of the input of the system, and you get the corresponding output. So you design your frequency response to give you the desired output. Okay, so please read the remaining material from the textbook, and I will also be sharing some problems later on. Thank you.